Awesome. Thank you, Ali, for inviting me. Yeah, so today we're just going to talk about our main part of this talk will be the connections between fully augmented links and fundamental shadow links, but we'll also get into the tri-zero volume conjecture. Okay, so this is the outline of the talk. So we'll start with introductory knots and links in three manifolds, and this is where we will discuss the connections between these two families of links. And then we'll get into quantum invariance of knots and then quantum invariance of three manifolds. Okay, so let's just start with the basics. A knot is an embedding of a simple closed curve into a three manifold. A link is just an embedding of a disjoint union of a finite number of these simple closed curves into a manifold. Ambient isotopy this is where we're going to consider knots and links up to ambient isotopy. So ambient isotopy is the continuous deformation of a knot in the manifold such that the knot never intersects itself. We're particularly interested in invariance of knots so that we can tell them apart. And an invariant is some quantity with the following property. First of all, it has to be defined for all knots or links, and it must be unchanged under ambient isotopy. That is, if two knots are ambient isotopic, then let's say K and K prime, then PK is equal to PK prime. Okay, so Reidemeister in the 1920s, I believe, showed that you can show ambient isotopy via diagrams. And this is like basically two knot diagrams give ambient isotopic knots. If you can go from one knot diagram to the other by a sequence of Reidemeister moves. And there's three types. So type 1 is just adding or removing a kink. Type 2 is sliding a piece of the knot under or over, or also the inverse of that. And Reidemeister 3 is sliding a piece of the strand over a knot or under, I'm sorry, not a knot, crossing or under a crossing, as shown in this picture. So we are particularly interested in fully augmented links. So first I'm going to define flat fully augmented links, and then I'll define what a fully augmented link is. So this is just a special class of fully augmented links. So a flat fully augmented link in the three sphere, or it's a link in the three sphere. And it has a diagram that consists of two types of components. So one type is knot strands, and the other type is crossing circles. So a knot strand are embedded circles that are embedded on the plane of projection. So these are all unknots, but they're going to be embedded on the plane. So this is shown here in the example in black. And crossing circles, these are going to be orthogonal to the plane of projection. And so it's going to also be an unknot where the disk that this unknot is bounding is orthogonal to the plane of projection. And you can see that here in silver. And also in particular, the disk that bounds this unknot of the crossing circles, they must also be punctured twice by the knot strand. So it is another property of crossing circles. Okay. So a fully augmented link, then, you can obtain a fully augmented link from a flat fully augmented link by inserting 1 or 0 crossings that are adjacent to the knot strand. So you're going to insert this crossing to the knot strand. Oh, sorry, not. You're going to insert the crossing to the knot strand that is adjacent to the crossing circle. So for example, or you can add 0 crossings, and that's this one here. This is just a flat fully augmented link, but you can add a crossing here that's adjacent to this crossing circle, which is shown here, or you can add it here, which is shown here, or you can add it to both, which is shown here. So all of these are examples of fully augmented links. Okay, so why would someone care about these? Well, one thing that we won't really discuss, but it is important in when studying fully augmented links, is that you can obtain fully augmented links from augmenting any knot. And what we mean by that is that when you have a twist region of a knot, you insert an unknot in that twist region and then remove all crossings, well, almost all crossings. You remove an even number of crossings in that twist region until you get 1 or 0 crossings. And the result will be a fully augmented link. In particular, though, what we're interested in is hyperbolic fully augmented links. And these are fully augmented links whose complement are hyperbolic. And so what is so one nice feature is you can you just need 4 properties of a fully augmented link, or there's only 4 conditions that need to be held in order for this fully augmented link to be hyperbolic. So the first condition is that you must have at least 2 crossing circles. The second condition is that the link must be connected. And the third condition is that the link must be prime. And finally, the fourth condition is that you cannot have any parallel crossing circles. So meaning to turn this into a fully augmented link, you can't put 2 crossing circles in this area. And also sometimes when you augment, you might get 2 pieces that actually, 2 pieces of the region that actually you can pull the crossing circle over and to the other region. And in that case, you don't want that. And that can actually be fixed by doing like flight moves. Okay. So one really nice feature about fully augmented links is that there's a very nice polyhedral decomposition of the knot complement. And this is given by Ian Agel and Dylan Thurston. So I'm going to describe this polyhedral decomposition in this example. So what you do is you start off with your fully augmented link in its diagram that it is defined on. And then you want to consider the disk that bounds the crossing circles as such. And then you're going to do 2 different things. So you're going to cut along the discs, and it's going to remove. So it's basically going to give you 2 different parallel discs, which you can kind of see here, but there's actually 2 things going on from here to here. And then from there, you want to remove all crossings that are adjacent to the crossing circle. In this case, we don't have any, so we did nothing. And then you want to cut along the plane of projection. And so that's what this is showing here. So it's showing that I've cut along the discs, and then I've cut along the plane of projection, which cuts the diagram into 2 pieces. And I'm only showing you 1 piece. So the 2 pieces, though, are the same, or they look the same. And so we're only going to focus on 1, but whatever I do here, you would do with the second piece as well. So the next step is to now you're going to glue these pieces back together, but only along the knot strand. And then what you're going to see is you kind of have like a pita bread when you do that, when you connect this piece to this piece and this piece to this piece, and you're going to have a hollow piece like a pita bread. And then you want to just unfold the pita bread, which is shown right here. And then after this, just note that what we're doing is we're looking at a polyhedral decomposition of the knot complement, which means that the strands are actually not in the manifold. And so now what we're going to do is for all the strands that you see here, we're just going to start contracting them to a vertex, and that's shown in here. So you see this piece is this vertex, and this one is that, and so on. Okay, now what we have is an octahedron. And remember, I said that we actually had two pieces. So we have two octahedra. Um, yeah. So that is the polyhedral decomposition of this specific fully augmented link. So a nice lemma from Jessica Purcell is the following. So the polyhedral decomposition, the complement of a fully hyperbolic fully augmented link, these correspond to circle packings of the two sphere. And they have a nerve that is a triangulation of the two sphere. This nerve has the following properties. So each edge of the nerve is distinct or has distinct endpoints, and also no two vertices are joined more than one edge, joined by more than one edge. Okay. For example, this is an example of how you get a nerve and the circle packing. So let's just go back here because this is the example. So this is the fully augmented link that we are considering in this example. And notice in the polyhedral decomposition, we get two octahedra. Okay, so we're just going to look at one of the octahedra. This, if you take these pieces and you kind of deform them into circles, and also this piece here and such, you're going to get this circle packing. This circle packing has this nerve here. So you get a nerve by connecting. So you're going to put vertices on the circles and then here, this outer area. Because remember, this is circle packing of S2. So you also have a circle out here. So you're going to put vertices in the middle of the circles, and then you're going to connect them by edges. And that's going to give you the nerve. Okay.
So, Dionne,
Yeah.
what is the nerve exactly here? The triangulation or?
Yeah, it's a triangulation of the two sphere, and you get it from your circle packing. And vice versa. You can also get, if you have your nerve, you can get your circle packing back by you just put vertices in the circles. And in case here, you would put circles on the vertices. And then each edge tells you where the circles are tangent. So circle packing is circles that are tangent at one point. Sorry, when they intersect, when two circles intersect, they intersect at the point of tangency only. So yeah, you can go one from the other. But yes, this is a triangulation of the two sphere.
Okay. Nice.
Okay. So Jessica also proved, I think this is maybe a piece of this actually, this lemma. So, oh, sorry, no, this is a different lemma. So suppose we have a triangulation of the two spheres. This is where I was saying you can go back and forth. Suppose we have a triangulation of the two sphere with the following properties that this nerve, so the same properties that satisfy a nerve, right? Then if you choose a collection of edges such that each triangle of your triangulation meets exactly one element in the dimer, or sorry, one element in this collection. This collection is now called a dimer. Then there is a hyperbolic fully augmented link that's associated to the graph. So what it's saying is like, so you have a graph, right? But you actually need a little bit more information to get back to your link, to your fully augmented link. And that extra information is this choice in a dimer, this choice in a collection of edges. But this choice also has some restrictions, right? The restriction is that every time you see a triangle, you should only see one dimer in this triangle. There cannot be two edges in this collection for one triangle in your triangulation. Okay, so when you have this, just want to double check everyone's here. Yeah. Okay. So when you have your triangulation and your dimer, this collection of edges, then you can obtain your fully augmented link. And you do that by this picture here. So for each dimer, you add a crossing circle. And then the crossing circle has two parallel strands that are going to come from your knot strand. And then also the triangle is telling you where these strands connect. So the triangle that's not, the edges of your triangulation that's not a dimer will tell you how to connect the strands together. Okay. Right. And then, of course, this is associated to this. So, um, okay. Okay, so we actually care about a very special fully augmented link. And this is called octahedral fully augmented link. And a octahedral fully augmented link is just a fully augmented link with polyhedral decomposition obtained by gluing regular ideal octahedra. So a regular ideal octahedra is just an ideal octahedron or regular ideal octahedron is an ideal octahedron in hyperbolic three sphere with all dihedral angles equal to pi on 2. And when I say ideal, it means you're truncating all the edges of your polyhedron. Okay. So one proposition that's very important to connecting octahedral fully augmented links to fundamental shadow links is the following proposition. So Jessica proved that if you have a nerve, let's say N, is a nerve of a circle packing that is associated to a an octahedral fully augmented link. So if N is circle packing associated to octahedral fully augmented link, then N is obtained by central subdivision of the completed graph. And you can go both ways. So if and only if. Okay, so what do I mean by, let me just explain this a little bit. So you start with, essentially what this is saying is that starting with completed graph on 4 vertices, which is shown here, you can get any fully augmented link from this by central subdivision. So essentially any subdivision of these triangles and so on will give you a nerve of a circle packing, and that will be associated to a octahedral fully augmented link. And not only that, you should be able to get all of them just by central subdivision. Okay, so let me just show you what happens when you do central subdivision on the nerve. So suppose you have this graph. So we're actually starting with the completed graph on 4 vertices. And then you do a central subdivision, let's say on this triangle here, which is shown here. That is associated to, so we first have this circle packing, right? And this is the nerve. When you do the central subdivision, say we do it here, what that does is it is changed by inserting a circle on the triangular face of your circle packing that is associated to the triangle that you're subdividing, right? So here's where, this is the triangle of the nerve that we are subdividing in this region here. This is the triangular region of your circle packing. And then when you do the subdivision on that triangle, you insert a circle. And of course, these circles are tangent to the circles that make this triangular face here. Okay, so essentially when you do the subdivision, you change your circle packing in this way. Okay, so this is going to be important in the near future. So what I want to do is I want to move on to shadow links, and in particular, fundamental shadow links. And then we will discuss how these two families are the same or give homeomorphic manifolds. Okay. So in order to talk about fundamental shadow links, we need to talk about dense surgery because these links are links in a 3 manifold that is not S3. So in order to describe a link in a manifold that's not an S3 on a diagram, we need dense surgery. So dense surgery is the process of removing a tubular neighborhood of a knot. Let's start with a knot. So you remove a tubular neighborhood of a knot. In that case, you have two pieces. You have the knot complement and you have a solid torus. And then you're going to glue the solid torus back in to the knot complement by gluing the two boundaries together. And when you glue the two boundaries together, the gluing map there, this homeomorphism, is completely dependent on gluing a piece of the meridian along the boundary of your manifold, the knot complement. And so basically, it is completely dependent on this circle, on this curve in the torus. Now, due to the fundamental group of the torus, we can describe this curve in terms of the generators of the torus. So PQ. P is the number of times the curve goes around the meridian, and Q is the number of times the curve goes around the longitude. We will consider longitude as the canonical longitude. And yeah, so that gives you a way to describe this curve. And so with dense surgery, what we do is we'll just turn that into a fraction, P over Q, and that will describe C here. So one thing we won't use, but is a interesting, nice result by Licorice and Wallace, is that, so they prove that every closed orientable three manifold can be obtained from the three sphere by performing integral surgery on a frame length, meaning that Q is equal to 1. So really it's only dependent on P, the number of times the curve goes around the meridian, and it'll go around the preferred canonical longitude only once. Okay, but as I said, we actually won't really be using that. And in fact, the first example, because I want to give you examples of three manifolds in terms of diagrams. The first example is not integral surgery. So the first example is S3. So you can describe S3 using a knot, the unknot, and you're going to do dense surgery along this unknot by -1 on P. So in this case, I think I accidentally flipped it. P over Q, sorry. So then this is the meridian, and then this is the number of times it goes around the longitude. And so for, let's say S2 cross S1, that is dense surgery along the unknot for 0 surgery, or so 0 over some Q. So it goes, and actually you would want to do 0 over 1, I believe, is the easiest one. Yeah, and so let's say we want to do connected sums now. We want to describe this using the diagram. So that is just disjoint unions of unknots with a 0 surgery coefficient. Right. But now let's describe knots in three manifolds. Right, and where the three manifold may or may not be S3, the three sphere. For example, in this example, this knot is in the three sphere. And this is because each piece that's describing the surgery is actually just the three sphere, as I've shown here. So we have two pieces. It has done nothing to the manifold. It does do something to the link if you want to get rid of these little unknot surgeries. But in terms of just the diagram, this describes a knot in S3. And you're doing surgery along these two pieces. Okay, but suppose instead I want to describe a knot, let's say in S2 cross S1. So in this is an example of that. So first we'll do surgery along this. This does nothing, as I showed here. This is just still gives me S3. And then I do surgery along this unknot with 0 coefficient. So that means that this manifold where this knot is embedded in is S2 cross S1. And also, this is the example actually that we care about. So if we have disjoint unions of circles with 0 coefficient, that describes the connected sums of S2 cross S1, and then you just put a knot somewhere in here, and that describes a knot in the connected sums of S2 cross S1. Okay. Okay, so finally, we can now talk about fundamental shadow links. So a fundamental shadow link is a link in the connected sums of copies of S2 cross S1. And these are going to be built out of, we're going to call them building blocks. And these building blocks are a collection of 3 balls that's shown here with 4 disks that's shown here on its boundary and 6 arcs connecting the disks. So that is shown here in brown. Okay, this building block is associated to this piece of the link. So notice, so for each part where you have your disks, that is associated to the unknot with 0 surgery. But you can also describe these building blocks in terms of a graph. So that is like basically this piece, wherever this is connected, it would tell you how to connect this part of the building block and so on. Okay. But these building blocks, they have interesting properties. So the building block of a fundamental shadow link is homeomorphic to a truncated tetrahedron, which I'm showing here, right? But if we truncate maximally, that means that we are removing all the edges. So we're like contracting all the edges to a point. This gives an ideal octahedron, and that's shown here. So essentially what this is showing is that the fundamental shadow links are built out of ideal octahedra. Okay, so now so far what I've shown is this family of links in connected sums of S2 cross S1 that are built out of ideal octahedra, and then I also showed you a family of knots in S3 that are built out of ideal octahedra. And so now what I want to do is I want to connect these. Oh, a few more. I guess I want to talk about a few more things. Sorry, but I do want to connect these two families. Right. So here I'm actually going to want to describe to you how these building blocks work. So the building blocks, they're glued along the disks, which is what I kind of showed with the graph. Yeah, so these graphs are going to tell you how you're going to glue along the disks. And then what this does, though, as you see here, what it does is it gives you arcs in a handle body. And then these unknots, these 0 coefficient unknots, these are telling you to double. So you have a handle body. It may be non-orientable, and then you're going to want to double. You want to take the orientable double, of course, because you want an orientable manifold. And what that will do is now that will take you to a knot or a link in the connected sums of S2 cross S1. Okay. And then this is another example too of what the graph looks like and how the edges will tell you how to glue up your building blocks. Okay, so one thing I want to mention is that Wang and Yang used topological arguments to prove the same result that I proved with Purcell and McQuire. So what we did is we used purely geometric arguments here. What we proved is that if we have if L is a octahedral fully augmented link with C crossing circles, then the link complement is isometric to some fundamental shadow link. And in particular, some fundamental shadow link where the connected sum is over C copies of S2 cross S1. Okay, so first I just want to show Wang and Yang's argument. Well, not really the argument, but the move that they use in their argument. So this is actually like a really nice move that where now you can just diagrammatically go from fully augmented links to links in the connected sums of S2 cross S1. So anytime you see a crossing circle, you can change that into an unknot with zero component where you add in a little unknot at the end that's connected as such to the unknot with the zero component or zero coefficient. Okay, so what we did is we proved this almost constructively. So we first start with the base case. So we showed that any fully augmented link of the Borrmean ring family corresponds to a fundamental shadow link with associated graph of the building blocks consisting of a single vertex and two edges that are loops. So maybe I didn't show that, this guy here. Okay, so this is the Borrmean ring family. And these are all octahedral fully augmented links. And in particular, all of them correspond to this nerve here. Okay, so for this nerve, we have the following circle packing. And the dimers of this nerve actually also tell you how to glue these triangular faces in the circle packing. So remember the circle packing, these are just octahedral pieces. And in fact, so this is one octahedron. If I, and I'll also explain this a little bit later as well. If I do a central subdivision, I have like another piece of an octahedron that's glued to this octahedron. But let's start with this lemma is just the Borrmean family, which is just, we're looking at one octahedron. So as I said, these dimers here tell you how to glue the faces. So it's glued by folding this vertex here, folding along that vertex here. So you're going to glue here, these two faces together, and then these two faces together, as shown in the dimer. Okay, so this is for the Borrmean family. So what is the difference? Because so far I just said that this is associated to all four different ones. Well, the difference is if you have a crossing adjacent to a crossing circle, then when you glue the two faces, you're going to glue it along reflection first. So you reflect and then you glue. If there are no crossings adjacent to the crossing circle, then you just glue just by folding, no reflection. Okay, so that's how these are different, or how you can get different fully augmented links for the same nerve and dimer. But now let's look at the fundamental shadow links. So the fundamental shadow link is obtained by a building block, right? And this building block, you can think of it as a truncated tetrahedron, right? And that when you truncate fully, you get your ideal octahedron. So this is our ideal octahedron. Now we're going to uncontract some of the edges to get our truncated tetrahedron. And notice that this is now telling us we glue here to here, which is what I'm showing here, and then here to here, that's these two pieces. But that is associated to having one building block in your associated to a fundamental shadow link where you're gluing these two edges or these two faces and these two faces together, which is corresponding to this graph. And in particular, so again, for fundamental shadow links, when you glue it, you actually have a choice. You can either glue just along, like folding this edge here, or you can reflect and glue. So that could be described by maybe decorating the edges. Right. Okay, so this is how I'm showing the correspondence of them. Now we want to now build on this. So we're going to use Jessica's proposition that tells us that we can get to any octahedral fully augmented link by subdividing this graph here. Okay, so let's see what happens when we do a central subdivision. So first, recall when I discussed this before, I had mentioned that when you do a central subdivision of the nerve, that adds a circle to the face of the triangle associated to the nerve where you're doing the subdivision. So suppose that this is the piece here. So we get a circle here. Now, at some point in the fuller picture, I also mentioned that we had dimers, and you can kind of associate this dimer in your circle packing as like some distinct edge. And this distinct edge tells you how to fold or how to glue. So this is telling me that I'm gluing this face that you can't really see and this face together. But when I did the central subdivision, notice that this face is no longer glued to the face that was here, right? So what had happened was you cut open this face, and then you add another octahedron. So that octahedron is shown here. So you have added another octahedron by gluing a face of the octahedron to this face here, triangular face of the octahedron to this face here. And then another triangular face of the octahedron is glued to this face. And then the two extra pieces are glued together. So diagrammatically, what that looks like is the following. So you start off with your, now we're just looking at the piece, one little piece of your nerve with the dimer. And now I'm going to do a central subdivision that's shown here in gray. Okay. Then what we do is note that when you have like a nerve with a dimer, the dimer must be an edge of a triangle where it is the only edge, right, of this triangle. You cannot have more dimers in a triangle. So this is actually forcing this edge to be a dimer. You cannot choose this one because of this triangle here. Can you choose this one? Actually, I'm not sure. No, you shouldn't be able to choose this one because this comes from another piece that would have a dimer. And
So
the same thing here.
So there's only one place where you can do the central subdivision?
No. There's only one place to put a dimer when you do the subdivision.
Okay,
So what I'm saying is like, yeah.
But you could choose a place to the central subdivision, right? And that will give you another dimer.
Yeah, yes, that is correct. Yes, but each central subdivision gives you one dimer, and that one dimer, you have no choice. It is chosen by the choice in triangle that you've done your central subdivision. Yeah. So okay, so this dimer must be here on this edge. And recall that I said earlier that the dimers are telling you where the crossing circles are. So you have a crossing circle here, but that was already here. There's a crossing circle here. Now we've added this one. And the edges that are not dimers are telling you how to connect the rest of the knot strand. So you must have two knot strands intersecting this crossing circle, and then the edges here are telling you how to connect them. Okay. So that is for fully augmented links. Now, what does that mean in terms of shadow links? So this is actually a graph move now. So we showed that this central subdivision in terms of shadow links is taking an edge of the graph that is corresponding to your fundamental shadow link and adding in a one gone. So you're adding a vertex and a one gone. And now, okay, so we're gonna show the same way that this is being glued. What this tells me is that I have now removed a face. I've unglued a face that was glued up before in the fundamental shadow link. Because remember I had mentioned that these edges are telling you how these blocks are glued. So first thing I'm going to do is remove that gluing. And then I'm going to add this piece in. And what this piece is telling me is I'm adding in one block, only one block, right here. So I'm adding in a block, and for two faces of this block, or the two discs of the block, will be glued to the pieces that were unglued. And now I just want to go back to here. What that meant in here was, I remember I had these two faces glued, but in order to get this, add this octahedron, I had to unglue the faces. And then I glued one piece of the triangular face to this piece here that was unglued. And then I glued this little piece to the other piece that was unglued. So far it's looking the same. Then the last piece is I glued the other two faces together. And that's what you do here as well in the shadow link. So this is associated to this graph move in the shadow link. But in particular, this is also, wow, okay, I'm going really slow, I think. But this is associated to the following diagram of your fundamental shadow link. So this piece here will kind of stay the same. And you can kind of see that here. So this was originally glued to this. And now when we've added this block, you have this arc is glued to this piece, is glued to this piece. And so that is associated to this blue arc. Now, this piece, originally, it went from here and glued to this piece and out. But now it's going to be glued to this piece, then this piece is glued to this piece, and then you go here and it's glued back. So it's going to come back around. And the same thing for this piece. It's going to come back around like this. And when you glue two pieces of the blocks, two faces in the block, you have to add in a zero coefficient unknot, right? So that is shown here. You have this zero coefficient unknot. This little circle here is associated to this strand here that's being glued to itself, causing an unknot. Okay. Okay, so this is, I guess, a long explanation of why these two manifolds are homeomorphic, or these families are homeomorphic. Okay, so now, after a long time, we're going to get into invariants of knots. And one invariant that we care about is the Jones polynomial. So this was discovered by von Jones. And I'm just going to define this using a scaling relation. So you have two conditions. First is that the unknot alone is just one. And then, and also you are saying that this is an invariant of oriented links. And then you have a scaling relation. So where D plus is the positive crossing, D minus is the negative crossing, and D0 is smoothing. Okay, so, right. But this is related to another invariant called the Kaufman bracket. And I believe I'll show how they're related. But the Kaufman bracket is it is not invariant of knots. It's an invariant of, or links. It's an invariant of framed links or knots. So a frame link is an embedding of a disjoint union of analy now in a manifold. And in particular, we really care about when the manifold is S3, because now we can associate a framing number to that by the number of, by the Reith of the knot. So you can essentially embed it into, you can take the diagram and you can embed it onto the plane where you will have your normal vector on your analysis, pointing orthogonal at all times, orthogonally up at all times. Okay, so we're going to just define the unreduced Kauffman bracket. And so unreduced means that the empty link is 1, and the unknot is negative a squared minus a to the negative 2. And then you also need 2 more axioms, and that's the disjoint union of a diagram with the unknot is the Kauffman bracket of the diagram times the negative a squared minus a to the negative 2. And also you have this nice skein relation. And I just described what blackboard framing is. So yeah, so this is how we can describe frame knots in as diagrams. But also now we can say what the framing number is by just calculating the Reith of this diagram. So to calculate the Reith, though, you must also have an orientation of your knot. So you orient the knot, and then you're going to count. So you're going to take the sum of all the signs of the crossings. Yeah, and that'll give you the Reith. Now, after using the Reith, you can now show the relationship between the Kauffman bracket and the Jones polynomial. In this case, I had mentioned I was doing, I defined the unreduced, which is why you have this little extra piece here. So this piece is because of the unreduced definition of this Kauffman bracket. But this would be the relationship. So of course you need to orient your knot, which is how you would get your Reith, and that is also how you define your Jones polynomial. Okay. Okay, so another interesting invariant of knots is called the color-Jones polynomial. And this is sometimes called the quantization of the Jones polynomial. And so this is defined, we're going to define it using this unreduced Kauffman bracket. And in particular, we're just going to say you're going to make a knot, you're going to take a knot with 0 framing. So you take a 0 framed knot, and then it is defined by looking at Jones-Wendel idempotent, which unfortunately did not show you, but yeah, so you take the Jones-Wendel idempotent, the trace of the Jones-Wendel idempotent, and you evaluate that in the Kauffman bracket along the knot. And then you have this little extra piece here, extra sign. And this is just an illustration of what I mean. And then this is just illustrating the Jones-Wendel idempotent and how you take the trace of that along a knot. Okay. The reason why we didn't define this is because later on I'm just going to talk about the Chebyshev polynomials instead, which is related to the Jones-Wendel idempotent. So in order to define the color Jones for links, we need to describe what we call a multi-bracket. So this is a multilinear map. You take a link, a frame link, suppose it has k components in the 3-sphere, then you need to order this link into its component, or you need to order the components of the link. So once you do that, then you can define the multi-bracket. So let's say the ith entry of this multi-bracket is associated to the ith component of your link. And you're going to use the Kauffman bracket skein module of the analysis, so the knot, cross, and interval. And in fact, at this point, we're just treating this frame knot as an analysis. Right. And then you're going to evaluate this in terms of the Kauffman bracket skein module of S3. And sorry, I did not define that, but you can use, this is basically just the unreduced Kauffman bracket. Okay, but how do we get there? This will be easier to see. So, okay, first we order the components of your link. Then you're going to use a meta bracket to tell you how to decorate this link. So for example, if you have, and we're going to just do this on the basis because it's a multilinear map. So suppose you have a 1, then that tells you that you basically delete that component. And suppose you have Z, which is going to be associated to the generator of the Kauffman bracket skein module of the analysis cross an interval. Then that tells you that so if you have one Z, that tells you you keep your knot. If you have multiple, like Z cubed, that tells you to put 3 parallel copies of that particular component. And so this is just another example that it's a multilinear map. So you can just pull these out, and then these two, this A and this A inverse is just 1 out here. This just had an A, so that's just a 1, which means you delete that component. This is a Z, so that means that you just keep one piece, one copy of K2. And this is a Z cube, which means you put 3 parallel copies of K3. Okay. Then once you have that, once you know the meta bracket, you can define the ith color-Jones polynomial of a link. So it is, this I is actually not an integer. It's like a sequence of integers, 1 through K, where K is a number of components. So you're going to, let's say, color or decorate the components by the ijth minus 1 Chebyshev polynomial. And the Chebyshev polynomial is described by this recursive definition. So S0 of Z is 1, S1 of Z is Z, and then you have this recursive relation. Okay. Okay, so why, I guess, how are these all connected? Is the question. So I want to kind of talk about the connections between physics, Jones polynomial, quantum invariance, and hyperbolic geometry. So in the physics side, we have topological quantum field theory. And due to Edward Witten, he made a connection between the Jones polynomial and TQFT. And he did this by utilizing Tsuchiya Aine and Kono's work that showed that the Jones representation of the braid group are ones that arise when one decomposes the correlation function of two-dimensional WZW model in conformal blocks. Yeah, so basically what I get out of this is there is a connection between the topological quantum field theory and the Jones polynomial. But also in his work, he speculated that there should exist a 3-manifold invariant that is related to the Jones polynomial from the TQFT. And later on, Reshetkin and Turayev constructed this invariant. And they utilize the quantization of the Jones polynomial. And this is why the colored Jones polynomial, this is the colored Jones polynomial, and this is why it's called the quantization of the Jones polynomial. And then, okay, so how is this connected to geometry? Well, it's all conjecturally connected at this point. So there is a conjecture, this is the original volume conjecture, that the growth rate, the limit of the growth rate of the Jones polynomial for some root of unity is, and you're taking the limit using R, which is related to the root of unity, is the volume. And there is another conjecture, which we are going to talk about, that is relating the growth rate of the Turayev-Biro invariant to the volume. Okay, so this is what I want to discuss. I am well over time though. So maybe I'll just like hand wave some things. So this is the definition of the Reshetkin Turayev invariant. First of all, notice that I'm still using multilinear map, and this is like basically the same thing that I had described before, except that now the entries are this omega, and this omega is just the sum of Chebyshev polynomials. And Turayev and Biro defined their 3-manifold invariant using a triangulation of a manifold. And when their original definition, they just define it for closed orientable 3-manifolds. So you just triangulate your manifold. Each tetrahedron is associated to a 6J symbol. There's other pieces that are associated to the pieces of this tetrahedra. And the gluing of the tetrahedron will tell you how these are colored, how these 6J symbols are colored. This is just an ugly side of the definition of the 6J symbol. Right. So, but then later on, Walker, Turayev, and Roberts separately proved a relationship between the Triaviro invariant for closed orientable three manifolds and the Reshetikhin triav. But then later on, it was extended. The Triaviro invariance definition was extended to closed manifolds with cusps and also compact manifolds with totally geodesic boundary. And then also Chen and Yang proposed a conjecture, a volume conjecture for Triaviro invariance. And so that is this one here, that the growth rate is equal to the volume, or the limit of the growth rate is equal to the volume. In here, though, R must vary along odd natural numbers. So I'm just going to summarize some other things. For example, Detchery, Kalfajani, and Yang showed a relationship between the Triaviro invariance of link complements and the Color-Jones polynomial. So that's shown here, how they're related. They also, so the same authors plus Belletti proved this volume conjecture for fundamental shadow links. So this is where the motivation of the project had come from, is are fully augmented links, or which fully augmented links are related to fundamental shadow links. And in particular, are all octahedral fully augmented links just shadow links? And the answer was yes. All octahedral shadow fully augmented links are fundamental shadow links, but not all fundamental shadow links are fully augmented links. Okay, another example, another theorem by Belletti, Detchery, and Kalfajani is that Triaviro invariance of complement, and let's say not complements, where M is just some closed orientable three manifold, is related to what they call the relative Reshetikhin triav invariant. So this is related to the Reshetikhin triav invariant, but they've kind of extended it to not complements, essentially. And they use this theorem and this lemma here, basically saying pieces, some 6J symbols with very particular colorings, and those growth rates go to the volume of an ideal octahedron. Okay, so essentially the work that we did, also the work of Wang and Yang, proved that the Triaviro invariants also hold for octahedral fully augmented links. But we wanted to go a little bit further. But in order to go further, we had to put a condition that the fully augmented links have no half twists. What I mean by further is we wanted to prove it in a different way. So what we did is we used just this guy. So we used this formula instead of this formula. So we're now just looking at fully augmented links and proving the conjecture for fully augmented links without going to the fundamental shadow links. And this is probably too much, but this is how we did it. So we showed that certain pieces arise, and these pieces have a nice form. Essentially, they have this is the most important part, is the 6J symbols. Yeah, and so that was how we proved it. But there's another piece, like when we found a formula, this specific formula here, we were also able to prove a question that Detchery, Kalfajani, and Yang proposed. And that's this piece here, like, does the growth rate of this specific Color-Jones polynomial, what I mean by that is with the specific colorings of M, does the growth rate of that also, the limit of that equal the volume? And we were able to prove it as long as M varies over the even integers. Yeah, but so that was it. Thank you.
Thank you, Dio, for the great talk. Anyone have any questions regarding the talk?
So what was the answer to that question in the previous slide?
This one? This was a
Yeah.
yeah, I mean, yes, but yeah,
Yes.
well, maybe yes. Yes, with one condition, because they proposed it when M just does like M is unrestricted. It just doesn't vary over even integers. So we kind of said slightly yes. Yes, with the condition that M in the limit must vary over even integers. The thing is, like, there's some weird things going on with here. So like this choice in sign, it has to do with whether R is like, I forget, some 3 mod 4 or 1 mod 4. It must be odd. But yeah, you have this choice is depending on, yeah, whether R is 1 mod 4 or 3 mod 4, and that changes the sign. And that is very hard to show. Like here, once you pick an M for even, that's like telling you, I think, when it's 3 mod R or 3 mod 4 or something, when R is 3 mod 4. So it's, yeah, it's a bit, there's some technicalities that we think could easily be fixed, but yeah, this paper was getting too long. So we were happy with who we had.
So maybe in a future work, you guys will address that part, maybe.
Potentially, we did mention in the paper how it could possibly be like fixed. So yeah.
Nice.